Alright gang, hopefully you have read through and answered the first 3 questions on here. And so let's take a minute to, hopefully you remember this game. We played it back in the fall, and you had to play a matching game, and you picked pictures of things and pictures of famous people. So in this experiment, subjects were randomly assigned to one of the image sets, and then you were given time to complete the game. So hopefully you remember playing that. If you don't, click on that link and that should bring back your memories. So the first question is, why is it necessary to randomize the order of those 2 image sets? This is a very common question on the AP exam. They love to ask this question. Why is it necessary to randomize? The reason we randomize is to reduce the impact of potential confounding variables. For example, maybe someone is really good at matching games and they play them all the time, and so they're super fast. We don't want to compare them to someone who's never played a matching game before in their life. So that would be a potential confounding variable experience. So the goal for randomization is to try and create a sample that is representative of the population. And if people have different experiences with these games, it's possible that a sample that's not random would not be representative. So that's the first one. Describe a procedure which could be used to randomly assign the order of the image. Well, you could use anything for this. I personally would say I love the hat method, or you could also do something with coins here. You could say each person's going to flip a coin. If they get heads, they're going to do image set 1 first and then do image set 3. And if they get tails, they would do the opposite order. And you would continue that until you have half the people doing image set 1 first and the other half the people doing image set 3 first. And then finally, the vocabulary term from chapter 4 that describes this type of experiment, do you remember it? It is a matched pairs experiment. And it's called a matched pairs because the subjects are doing both treatments. So if a subject is doing both treatments and you're comparing the subject to themselves, that's called a matched pairs. So we're going to take these results then, and we're going to see if we can come up with a confidence interval to see if we can answer Mr. E's conjecture down there. So here are the results from 15 students last semester. The image set played first was randomly assigned. The data is given as the time required to complete, and you can see the different times and seconds for each one. My conjecture is that subjects will generally be better at the game where things are featured rather than people. So the first thing is, how can the data in the table be used to provide evidence towards this conjecture? Well, we're not comparing the 2 sets, things to people. We're comparing each person to themselves, and we want to know the difference. So the first thing we're going to need to do is we're going to need to create a new column, and we're going to call that column the difference. So we're going to subtract, and we can just do it in the order that it's given here. So 63 minus 72 is negative 9. And 74 minus 75 is negative 1. And 92 minus 87 is 5. And I'm just let you keep going with that, and you can fill these down as well. And I'm doing this very quickly, so hopefully I don't make any obvious glaring mistakes as I'm subtracting. And you can see that I'm just subtracting the things from the people. Some of them are positive, some of them are negative. It's like most of them are actually negative. And let's see, 17, so that's 18. That's 13, and then that's negative 1. So we want to know then, how can we figure out whether someone is better at this game? Well, if my conjecture is that people will be better with the things than the people, then my conjecture is that the things is going to take less time. So the things is going to take less time than the people. So if that's true, then that means that if I do the things minus the people, that should be less than 0. In other words, the difference should be less than 0. If the difference is less than 0, and let's be more specific, let's say the mean difference is less than 0, then that means my conjecture is right. So we need to come up with, let's see if we can create a confidence interval to let us estimate what that mean difference really is. And if our confidence interval shows that the mean difference is less than 0, then that would mean my conjecture is correct. And we would be able to say, hey, Mr. Evans is a genius. So let's start off with this. So we're going to use, let's use our 4 C's. So first we're going to choose, we're going to use a one sample t interval, because this is a means problem, so it's still t's, to estimate the mean difference in time needed to complete the puzzle. And I should make sure that I tell the grader the order. So I'm doing things, which is, I guess, I don't know what set it was, things minus the people. Alright, so that's the method we're going to use. It's one sample t interval. I will give you a little bit of a shortcut. A lot of times when I'm grading or looking at the scoring guidelines, they allow you to say a paired t interval. So if you don't want to do a one sample t interval, I just noticed I wrote interval twice, I don't need to do that. If you want to just say a paired t interval, that would also do the trick. So a paired t interval to estimate the mean difference. So our conditions are, I'm not going to write all these out just because I don't want this video to be 15 minutes long. The conditions are the same conditions that we've been dealing with. They have to be random. So they said it was randomly assigned. They have to be independent. Now, we need to be careful here. This is not a sampling. I didn't randomly choose these 15 people. So I can't say it's safe to say there's more than 150. I can't use that here because I'm not choosing these people. Instead, I need to say each subject is independent of the others. So make sure you note that, right? Each subject is independent. And then finally, normality. Normality is normally, funny, that's normality is normally. Normality, we would use the CLT, n is less than 30. But clearly, n is not less than 30 here. N is only equal to 15. So I can't do that. So instead, I'm going to have to use the box plot. So it would have been smart for me if I had had my calculator open before I started the video, because now we have to wait for my calculator to open up. But while we're waiting here, you can enjoy my nice picture of Iceland. That is Kirkjufell Falls and Kirkjufell Mountain in the background. People who watch Game of Thrones might have recognized it. All right, so anyway, so I digress. Let's see if I can make this a little bit small. All right, so we're going to go to second list. We're going to go to list. Nope, not second. Yeah, second list. Nope, just stat. Edit, stat, edit, list 1. And now I need to enter in the scores, the differences. So I'm going to put the differences in list 1. -9, -1. Oh, what happened there? Stat, edit, stat, edit, -9, enter. Oh, I didn't like my negative. All right, try that again. Stat, edit, -9, enter. All right, let's try it this way. -1, enter. 5, enter. 1, enter. -25. -3, 0. -5, 5. -11. -3. -24. -18. 13. And -1. Enter. And so now we can take a look at the stat plot. So second stat plot. Turn that thing on. Go down here. Choose stat plot. Enter. And do And there we go. So the stat plot, or the box plot, shows no outliers, no heavy skew, so therefore we can say normality conditions have been met. Our formula that we're going to use is the exact same formula you use for means, and in fact, we can use, go down here to a t interval, right? See, it's not a one proposition, it's a one proportion, sorry. It's a t interval. And I actually have the data, right? The data is in my list, so I can use the data, list 1, and let's make a 95% confidence interval. So calculate. And I get an interval of -11 up to 0.866. All right, -11. It's really crazy that that worked out to be exactly -11. -11 to 0.866. So the interval then is -11 to 0.866, and it has a degree of freedom of 14. And normality condition was met from the box plot. You should always draw the box plot, at least a sketch of it. And remember the way you approach that. The box plot shows no outliers, no heavy skew, so normality condition is met. The calculate part, we have our interval here, and then we can do our conclusion. And the conclusion is that we are 95% confident that the true mean difference in time is anywhere from -11, or is between -11 seconds and 0.866. So does that answer the question? My conjecture is that subjects will generally be better, and actually my conjecture might be wrong, because it is plausible that 0 is a solution, because 0 is in the interval. And if 0 is in the interval, if 0 is the true difference, then that would mean that there is no difference, right? So my conjecture is incorrect. There is no clear evidence to conclude that subjects are generally better at this game where things are featured rather than people, because 0 is a plausible value. So hopefully that helps, and now I'd like for you to try the mean difference homework. Good luck.